Okay, welcome to this video on the area of a circle. So this might or might not be something that we've spoken about in class before, but regarding the area of a circle, you know very well from our previous stuff about area that I like to talk about proofs and showing you why we use a particular formula for the area of some shape. So the circle is no different, and there are many proofs for the approximate area of a circle. Some of these we will investigate in class if we haven't already, but in this video I'm going to go through one of the better ones that will sort of come up and inform some of the mathematics you do later on in your maths career. But let's continue on. So in this video we're going to have a look at a proof and how to use the formula of a circle for the area of a circle. So let's look at this proof. Infinite triangles. So it sounds exciting. I hope it makes you excited. But what we've got here is a circle, good old circle here. And what I've done here is I've drawn a hexagon inside the circle and divided it up into 6 triangles. Okay, so 1, 2, 3, 4, 5, 6. Okay, so what we're doing here is we're trying to find the approximate area. Okay. Alright, we're not going to be able to find perfect because see these little pieces in here. None of these pieces here have, they're not counted as part of adding up the sum of these triangles. So what we'll end up with is an approximate area, which is 6 times half base times height. Because remember, half of base times height is the area of a triangle, and we have 6 of them, so the approximate area of this circle is 6 times half the base times height of these triangles. If this was the base length and this thing here was the height. Okay, so if we scroll down, right, what about an octagon? So what if I divide my circle up into an octagon? I want you to imagine that there's lines coming across here and here and here and here and making a terrible octagon. But you can kind of see that even though it's still an approximation, it's a better one. So we have less space, that's not being counted. Okay, so we're going to get a better approximate area. Better approximate area is in this way because we now have the area of our circle being approximately equal to, that's what this thing here means, approximately equal to 8 now times half the base times the height. Okay, so as we make more and more triangles, so we went from 6 and it was okay, we went to 8 and it was even better. So what if we went to 10 or 12 or 15 or 20 or 100 triangles? We would get really good approximations, even better and better and better. Wouldn't be perfect. What about 1,000 triangles or 1,000,000 triangles? Okay, so I want you to think about dividing this circle up into smaller and smaller and smaller triangles. Okay, so the general case for the area of a circle using triangles is, as we've seen, so remember, we'll just quickly scroll back up again. For the octagon, it was 8 times half base times height, and for our hexagon one, it was 6 times half base times height. So our general case for the area of the circle using triangles is, so our area of a circle using the triangle method is approximately equal to the number of triangles times half of the base times the height of those triangles. Okay, so however many triangles divided up into times half the base times the height of them. Okay, so now we're going to talk about doing something called the limit. Okay, so what we're going to do is, as we're going to increase the number of triangles towards infinity, so n goes towards infinity. Okay, so we'll end up with a different color. So the area of our circle will be equal to, what we do is this interesting thing called the limit as number of them approaches infinity. Number times half base times height. So some of this is a bit crazy stuff, but you'll see this thing later on in this thing called calculus, which is my favorite piece of maths, my favorite area of maths, okay? Right, so as we increase the number of triangles towards infinity, the base length gets closer and closer to 0. Okay, so just off to the side here, I want you to think about that when we had our hexagons, our triangles, you know, this big. When we had our octagons, the triangles are sort of smaller. And then as we're going to get smaller and smaller little slivers of triangles, okay? This base length gets closer to 0. See how the base length got smaller and smaller and smaller and really, really, really small as we got more and more triangles, okay? So as n goes towards infinity, more triangles, our base length goes towards 0. So what we have eventually is a whole circle full of tiny slivers of triangles, okay? So here's our circle, and we've got a triangle, 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 blah, 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 all the way around, okay? All the way around triangles. Tiny little slivers of triangles, infinitely many of them. So remember that our area formula was the number of triangles times half of the base times the height. Now, let's think about this base sort of number here, okay? This base is all the little dots of triangles sort of around here, okay? So if I added up all of this infinite amount of bases that go around here, what will I end up with? Okay, what would we end up if we added up all the little pieces of the outside of a triangle, of circle? We end up with the circumference. Okay, so instead of number of triangles times the base, we can say instead that becomes the circumference of this circle. Okay, times half times, now the height. Let's look at the height. The height of these triangles. If before, when they were like this, the height was this piece up the middle, so it didn't extend all the way out to the edge of the circle. But now, because we have infinitely thin triangles, it extends all the way out to the edge. So what is this length here called? It's halfway across the circle. It's called the radius. So instead of calling it the height of the triangle, we can call it the radius. So now the area of our circle is equal to the circumference times half of the radius. Okay, well we've got some radius stuff happening here. What's inside circumference? So we've already tackled circumference. So we know already that the formula for circumference is 2 pi r. That's probably the better one, like pi d is fine too. 2 pi r is probably what you will use more often. 2 pi r times a half times r for radius. Okay, well, we're starting to see some common values. So we've gone from formulas using triangles to now using an infinite number of triangles and getting down to this crazy thing. So a half of 2 is only 1, so just off to the side, just to so we know we're on the same ballpark. So 2 times a half equals 1, so we can cancel these two out because they get rid of each other. Okay, so we're left with the formula for the area of a circle is equal to pi r times r is r squared, and there we have it. There is our formula for a circle. So you might have already known that, but now you know where it comes from, or at least one of the proofs for it. There are others, and if we haven't looked at them in class, I suggest that you hop on the net and see if you can find a couple. Right, so let's have a look at using the formula for area. It's an easy one, just like the other area formulas. It's just plug and play, okay? So I've just got some circle here at 7 centimeters of radius, okay? So remember, radius is from the center of the circle down to the edge. So here's my formula that we just worked out before, that the area of a circle is pi r squared. We simply substitute 7 for r, okay? Now, you know that I usually like to have brackets, especially when I'm using indices, but you know, 7 squared, pi times 7 squared is 154 centimeters squared. Please do not forget this unit, okay? Remember, it's important. We're talking about area. We have to talk about this. If you just leave it as 154, doesn't mean anything. If you just have 154 centimeters, that's a length, not an area. You've got to have centimeters squared, because remember, it's radius times radius, centimeters times centimeters gets us centimeters squared, okay? So pretty much that is how you use this formula. Obviously, there's many other cases, including it in other composite shapes and things, but there it is standalone, exactly how to use it, okay? Thanks for watching this video.